All right, welcome Precalculus students. This is going to be a little different. I am recording this on my computer at home, obviously, which is a little weird. And we're going to review this week the first 4 days of Unit 8. Yeah, so let's just get started. I'm going to try to keep it under 45 minutes. And if it gets too close to 45 minutes, I'll probably start skipping some examples, and then we can just go over these in the class period time. But so let's go ahead and do number one here. So this is just a review of what domain and range is. So the domain of this piecewise function, we can see that it's broken into pieces. Here is going to go from, we use a parenthesis here because of the open circle. It's going to go from -4 all the way to 2, it looks like. It looks like the scale's going by 2s. We'll use parenthesis, union, and then it goes from 2 on to infinity. So 2 on to infinity. Okay, and the range, now on the other hand, only includes the y values here, and we want to start at the lowest y value first, which we can see that it goes down to negative infinity by this arrow here. So we're going to say negative infinity all the way up to right here is a positive 2, or negative 2. And we'll use a bracket there because that is a filled in circle. It's including that negative 2 in the range. And then the other y value that's included is up here at 6. So we want to use an isolated y value. I'm just going to use curly braces and use a 6 here. There we go. Let's do the same thing, for this next one down here below it. Um, Oh, I think that's the only one I gave for that particular example. I simplified the notes here. I cut out some examples so that we kind of get to see one of each. So this next problem is looking for the y-intercept. So this y-intercept right here, if the scale is going by ones, just guessing, so I'll just say a guess. If I were to have to guess what this is, it looks like the x value is 0. For y-intercept, you want a x value 0, and the y value is maybe like 1 1/4, 1.25, or 1 1/3, if I were to have to guess. Now, algebraically, though, we don't have to guess. You can just plug in 0. So for y-intercepts, so for the y-intercept, we want x equals 0. So you always plug in x equals 0. And so this is going to be -2, 0 cubed plus 4. So I'm using the function they gave us over 3. So this is going to give us 4/3. So my guess was wrong. It was 1.3 repeating 4/3. Okay, up here, so hopefully these notes I'll send out to you in the same way that you got the link to this, so you'll just pull up the notes for yourself. So if you want to print them out, or if you're able to print them out, you can. If not, you can just follow along here. This one wants the x-intercepts, so I can see there's an x-intercept here, here, and here. So if I were to guess, I would say the origin is an x-intercept. This one right here looks like maybe 1 1/3, I'll guess, so 1.3 repeating. Notice the y values are 0 for x-intercepts, and then that one maybe looks like 2. So I'll say 2 comma 0. Now, algebraically, we actually have to do the work here to find out what it is. So we want to let's see, did I say y equals 0 down there? I said x equals 0. So here we want y equals 0. So set y equal to 0 is what you want to do. So that means our function f is going to be 0. So 3x cubed minus 10x squared plus 8x. There we go. And so now we'll want to factor by grouping here. We can pull out an x. That leaves me with 3x squared. And then over here is a plus 8. And in the middle is a -10. So 3 times 8 is going to be 24. Factors of 24 that add up to be -10. That's going to be +2 and -12. So -12x plus 2x. And then we can group and factor out here. So let's go ahead and group the first two. So this, I'll use brackets here. You can pull out a 3x. And we're left with an x minus 4. And here we can pull out a 2. Uh-oh. Have I made a mistake? Plus. They multiply to give me -24. They sum to -10. Let me pause the video, figure out what I've done wrong. 3 times 8 is a positive 24, so the 3 and the 8 here we want is a positive 24, and we want the positive factors of positive 24 to add up to be 10. So let me fix that here. So this we'll get rid of. Okay, so what do we want? Let's see, factors of positive 24, that have to be negative 10, so maybe like negative 2 and 8, negative 3 and nope, negative 4 and 6. There we go. So negative 6 and negative 4. And then we'll group, so pull out a negative 3. What we're left with is x minus 2. Here we'll pull out a negative 4. We're left with x minus 2. So now that these x minus 2's match, I know that I've done my grouping properly, and then I can factor each one of these. So this is going to be x minus 2, and then 3x minus 4. So set each one of these equal to 0. So here's my roots, 4/3. And it looks like I was correct with my intercepts. So the origin is 1, 2, 0 is 1, and 4/3 is 1 as well. All right, on to the next one. Here, we're talking about intervals of increasing and decreasing. We saw this one in class. So negative infinity to right here. So this is, we're talking about the x values, so the x intervals. So all the way from negative infinity up to this point, negative 5, is where the graph is increasing. So I can use a blue highlight. Whoops. It's really hard to do this here. Let's see. So if I maybe use thicker pen, bear with me as I get used to this. So that would be the increasing interval. Now we want the constant interval, so constant interval would be right here. That's in between negative 5 and 0. So we'll put that down here. Uh-oh. So the constant interval is in between negative 5 and 0. So we'll write negative 5 and 0. And here I'm using brackets for intervals of increasing and decreasing. Those are technically proper, but if you use parentheses, it's not a big deal. Even in AP Calculus, they accept that. So here in this interval from 0 to infinity, we can see that the graph is decreasing there. So intervals of increasing, decreasing, and the most important thing to remember here is x is always going to the right. So x increases to the right. So as x increases, is y going up or down or staying level? So here y is going up, so y is going up. Here y is going constant, and here y is going down, so this would be decreasing. Okay, so let's go to the next page. So here I'm going to use a calculator, a Desmos calculator. I'll put the link in the video description or in the email that you guys get this video from. So let me pull up the calculator real quick. Okay, so the Desmos app looks like this. So I will send this to you. You can download it using Chrome. So what I'm going to do is plot this function here that we have on this Desmos calculator. Let me go ahead and type it in. So negative, this is y equal negative 4x to the 4th minus x cubed plus 3x squared plus 2x. Okay, so there it is. And now the wonderful thing about this Desmos calculator is you can just hover your mouse over the max and mins and it spits out the decimal values for you. So none of that left and right nonsense that we were doing on our TI-84. So this is much, much better. So let me go ahead and side by side these two windows so that we can do those together, just like this. Okay, and so here we want this point, well, let's see, it says where does the function have a relative minima? So let me pull this up. So minima, when they're asking about where in minima, this is talking about a min. So we're looking for this minimum value down here at the bottom. And so the word where, the key word, means that we're looking for x value. So that's an x value. Same thing here. Where indicates an x value. Whenever they say state the actual maximum min, they're referring to a y value. So state the is going to refer to y values. Okay. And let's go ahead and write down this one. We just want x equal negative 0.306. Okay, and same thing for max. There's going to be two, so I'm going to label them x1. This one right here is negative 1.52. I would normally go 3 decimal places. I think when Desmos rounds it like that, there's just a 0 there. So here, this is going to be 1.076. So x2 equals 1.076. I think that was right. Yep. Now, when they say state the actual minimum, so here we just want to say y equal negative 0.311. So y equal negative 0.311. And here we'll have a y1 for the max and a y2 for the max that correspond to our x1 and x2s from before. So it's 2.065. And this one is 3.039. Sorry, my writing is so poor, it's very difficult to write here. So here, sine we learned was an odd function. This is odd. That's the definition there. And cosine is an even function. And tangent is also odd. So these are the definitions of odd and even. So, I mean, if you want, you can highlight these. Those are pretty important. Now, in order to use those definitions, if you recall, our first quiz, we had that. So here what you want to do is plug in. So we're testing to see if this function is odd or even. Let me blow this up a little bit bigger. Ooh, I realized I missed part E here. What we want to say is concave up at, so right here, concave up at minimums, so that's at a min, and then we want to say concave down at max. Okay? And so that's just always going to be what our response is for this. I really don't care about the x values. It's just always going to be for algebraic functions. We'll just have concave up at minimums and concave down at maximums. It's kind of opposite of what you would expect. I would expect up is at a max and down is at a min. So that's kind of really what we're testing here is can you get that order correct? The curvature is up at a min and curvature is down right here at a maximum. All right, so down here, in order to test whether or not a function is odd or even, we want to plug in a negative x and then simplify. So we'll put in a negative x everywhere there is an x, just like this. And since sine is odd, that means that it obeys this property. It spits out the negative sign. So what we're going to do is we'll spit out a negative out of the sign. In x cubed, when you cube stuff, you multiply it to itself 3 times. So we have negative x times negative x times negative x, which 2 of the negatives cancel, and the third hangs out there. So it looks like this. And there is a minus sign in common between those two that I can pull out. So we'll pull those out. And then what I'm left with here is a negative g of x. So this is g of x. So that implies that this function is odd because the minus sign is now out in front. Now this one here, when I plug in the negative, we want to replace all the x's with negative x's. And we know from above, up here, cosine is even, which means that it obeys this property, so that it swallows negative signs. Negative signs disappear. So we can just take away this negative sign. inside the cosine. Cosine doesn't care about negatives, it's an even function. And then we're let right back to where we started. This is the original function g of x here. So now that implies this is even. Since cosine is even, then this function g of x is going to be even. And this one's directly off of our notes here. If you recall, we'll replace all the x's with negative x's. We'll factor out a negative in the denominator. The negatives cancel, leaving us with x over x plus 4, which is, this is not h of x, and it's not negative h of x. So it's neither one of these. So here we would say neither. Okay, so that's it for day one. Let's see how long it took. It took about 15 minutes. Ooh. So let's keep moving. So day two here, what did we learn there? We talked about end behavior and as the function approaches infinity. So we learned a little bit about limits of polynomials and rational functions. So here what we did is we took the limit as x goes to infinity of this function g of x. So we're learning the syntax here, what it should look like. First, you put the limit. X goes to, this tells me x is approaching infinity. It's getting bigger, so that's to the right. And g is the function. You should always have a function behind the limit. And that tells me the y values are going. This is always on the other side of the equal sign telling me where the y values are going. So the y values are going up as x goes to the right. So we want to say infinity here. Now, as x goes the other direction, so negative infinity of g of x, we can see that the y values here are going down. So we want to say negative infinity. This next problem here, number 2, as x goes to the right of our function f of x, we can see that it's approaching some kind of value right here. It looks like it's maybe a horizontal asymptote there. And if you were to have to guess by the graph, I would say maybe 4. But looking at the function, looking at the ratio of the coefficients here, 3 over 1, remember, if you have, oh, erase that. If you have the powers that are equal, you look at the coefficients. So this is a limit of 3 is the proper value there. And as x goes to negative infinity of the function, it also approaches that same horizontal asymptote of 3. Again, that's because we're comparing the powers of the function. Here, polynomials. They want us to graph here using the Desmos calculator again, so you will be able to use these, so don't feel bad about plotting it. So we'll just say x cubed plus 3x squared plus x plus 3. And here we can use this to help answer these questions. So it's really, you don't have to graph it. So we'll just go ahead and kind of go back. Let's see, I'll split the screen again. So we'll go like that. So polynomials always have a domain of all real numbers. So we're going to say negative infinity to infinity. You could also use the double script r. The range for this cubic, we can see that it covers all y values. So we're going to say negative infinity to infinity as well. Let's see, this limit here is asking for the right end behavior. So as x goes to the right, it looks like the function's going up to infinity. So that cubic graph is going up to infinity. And here, this one I think is a negative. Oh, this one was the negative. So this one's going down on the left. Right here, the y values are going down. And this one on the right is going up. So infinity right here. X-intercepts, if I hover my mouse over this, it'll tell me. That's nice. So negative 3, 0. Y-intercept, that's also nice. I can, the minimum is very close here, so make sure you've got the right one. That's 0, 3 is the y-intercept. Interval of increasing, it's going to be increasing all the way up to the maximum. So maybe let's write our maxima and minima first. So I've highlighted the maximum over there. So let's go ahead, and you don't want to write the ordered pair. The maximum is the y value. So what I'm going to say is f of the x value equals the y value. So I'm looking at that point that I've highlighted over there on the right. So that tells me f of, this is where the maximum occurs, and over here, this is what the maximum is. So the maximum is 5.089. And now the minimum is going to be f of, so let's highlight that one, that's right here. It'd be nice if I could keep that highlighted. I don't know if I can do it like I did before. There we go. So this one is going to be negative 0.184, and the y value is 2.911. Okay, so now the reason that I like to write it in this notation is so that we can easily get our intervals of increasing and decreasing. The function over here is increasing all the way up until the maximum. So I'm going to say from negative infinity, it increases. So you always start with the lowest x value. So negative infinity all the way up to this value right there, negative 1.816. And then it starts decreasing from there, and then once it reaches the minimum, which is at this negative 0.184, it continues increasing after that point. So that's what we want to write here. And then we want to, for our decreasing interval, we'll do something similar. We just want this bit in the middle. So we want negative 1.816. So to 0.184, just like that. Where does the function have a relative minima? Well, the where is the x value. So we want to say x equal negative 0.184. Again, you can use either parentheses or brackets on these increasing and decreasing intervals. It doesn't really matter. And whenever it's asking a where, they want an x value. Concavity at extrema, concave up, at min, concave down, at max. Function even, odd, or neither. Let's go back and look at it. A good way to tell whether or not a function is even or odd. Even function should be symmetrical about the y-axis. So in order for this to be even, it would have to have another hump going down here. So it's definitely not even. In order for it to be odd, it would have to be symmetrical about the origin, which means if I flop the points, the graph should basically rotate or mirror image down to the other quadrant. So the graph should be down here. It should be mirror image. This point would be down here somewhere, and it doesn't really mirror image, so that's not odd. Another way to tell odd is, so rotational symmetry is one way, and then flip-flop. So flip it down over the x-axis and flop it over the y-axis. So this one happens to be neither. So horizontal asymptote rules, I think you may remember these. So numerator degree. So if the degree of the numerator is greater than the degree of the denominator, then that is no horizontal asymptote. If the degree of the denominator, we'll say numerator here, keep it consistent, is less than the degree of the denominator, then horizontal asymptote is y equals 0. And if they're equal, so if the degrees of the numerator equal degree of the denominator, then we look at the ratio of coefficients. So I'll say ratio of coefficient. So it's a over b. So y equal a over b. Maybe I should write that there. So y equal a over b is the horizontal asymptote. Okay, so these are the three rules. Hopefully you remember those. We did them at the beginning of the year. Some of you may remember this as Leghorn, I think. Let's see if I remember Leghorn. Less than, numerator less than the denominator, y equals 0. If they're equal, you look at the ratio. So this L stands for less, and the E stands for equal. So you look at the ratio. Greater than, numerator greater than the denominator is the corresponds to the N. So that is, what does that stand for? No horizontal asymptote. I've never really used that, but I know a lot of you use that. So, um, but there you go. So the H, I think, just stands for horizontal asymptote. So make sure that horizontal asymptote, you always have y equal. So it's either 0, ratio, or none. Okay. Well, let's keep going. We might skip over some of these just because we are uh, already approaching our time limit. We have some time, but I want to have plenty of time here. So let's go ahead and do this next one here. What are they looking for? They want us to answer these questions. You may use a graphing calculator. I'm going to do as much as I can without one. So let's go ahead and write this down and factor the denominator. I think we want a positive 3 and a negative 1. So the domain is going to be all the values except where the denominator is 0. So if we set the denominator equal to 0, we're going to get x equal negative 3 and x equal 1. So those values are where vertical asymptotes are. So at negative 3 and positive 1. And so we want to exclude those from the domain. I really don't care how you write this. It doesn't really say interval notation, so you could say all real numbers. X is not negative 3 and 1. That's one way to do it. Or you could use interval notation all the way to negative 3 to 1, and then from 1 to infinity. That's a little bit more painful to write. The range here, you really need a calculator probably to determine that. But if you look at the ratio of the coefficients here, since the powers are equal, it looks like we're going to exclude y equal 2 as a horizontal asymptote. So you'd probably want to graph this on a calculator. I can do that real quick. I'll pause the video and graph it. Okay, so here's the graph. And you can see that the y values that are missing are between this maximum and the horizontal asymptote that occurs at 2. Now, here you can't quite tell that it's at 2, but it is. Here's a minimum at 1.5. So we have a min at 1.5. That's very unique. And a maximum at 0, 0. Let's go ahead and write those down. So the minimum is at f of, I think it was 1, so 3 and comma 1.5. So this is 3, f of 3, 1.5. And the maximum was at the origin. Yes, the y value of the max is lower than the y value of the min. It's because it's a broken function or a discontinuous function that can happen. So the graph looks something awkward like this, where it comes up. And then here it actually dips below the horizontal asymptote and approaches back. This side, I think it just comes from the top, like that. So here, the range, we have to be careful here. It excludes all y values in between the max and min. So there is a gap in between this maximum and that minimum. So we're going to say negative infinity. So all the y values up to 0, and then from 1.5 up to infinity. X-intercept, well, there is for sure one at the origin, because that's where the maximum is. It crosses the x-axis, touches the x-axis. The y-intercept is also the same, and we didn't see any other x-intercepts on our Desmos graph. Intervals of increasing. So this side of the graph, it's increasing from negative infinity all the way up to this vertical asymptote here. So we're going to say negative infinity up to negative 3. And then it continues increasing after the vertical asymptote, negative 3 up to the maximum, 0. And then it does increase after this minimum here. So it comes down from the vertical asymptote to the minimum, and then it starts increasing there. So we want to say from 3 on to infinity, it's increasing. So the decreasing intervals are just going to be everywhere else. So we want decreasing in between, let's see, 0 to, let's put in the vertical asymptote at 1, and then 1 to the maximum, or the minimum there, 3. So 1 to 3. So it's right in here is that decreasing interval. Yeah, and there's a break in the decreasing interval with that vertical asymptote. Concavity, concave up at min, and concave down at max. It's easy to get that backward, so try to keep that straight. Is the function even, odd, or neither? There is no symmetry in the function at all, so we want to say neither. The limit as x goes to negative infinity is 2. Limit as x goes to positive infinity is also 2. How do I know that? Well, I looked at the ratio of the coefficients. So the ratio of the coefficients tells you the horizontal asymptote. And remember, the way to determine the horizontal asymptote is one of those 3, or that Leghorn rule. So that's how I remember finding horizontal asymptotes or answering these limits at infinity. Vertical asymptotes, there are 2, one's at -3 and the other's at 1. Okay, let's do this next one here. So this is moving on to day 3 notes. I think this is a plus, and that's an equals, and this is a minus. So this is composition of functions, if you remember doing this. So this is the product of 2 functions. This is the quotient of 2 functions. So this is just new notation. It's really nothing new here. We've done this before. I think this may be a minus between those 2. It's hard to tell. And I can't tell there. We'll just say a minus as well. So the product of 2 functions, you just write this dot in between the 2 functions is indicating a product. So we'll write f. This is our function f. And then we want to multiply that to g, which is the square root of x plus 1. So here's g. So f and g, whoops, we want h, not g. Let's put in g there, or h. So 2x minus 3. H. They do say simplify or determine the domain of the new function. So let's go ahead and simplify this. Maybe you can distribute. Yeah, do we want? Yeah, let's go ahead and do it. So this is going to be 4x cubed, 6x squared minus 2x plus 3x plus 9 minus 6x. Yep, I foiled these. That's a little bit of work there. Let's condense it. So 4x cubed minus 6x squared. We have a total of minus 5x's. Okay, the domain of the new function here, all real numbers. Polynomials take all real numbers. So the product of a polynomial with another polynomial is just going to be all real numbers. Now, this one, the quotient, on the other hand, has a restriction of domain. So for a couple of reasons. So the denominator cannot be 0. So here, this right here is g, and down here is h. So g has a square root. So the inside of the square root, x plus 1, always has to be greater than or equal to 0. So that restricts x. It has to be greater than -1, so I subtracted the 1 to the other side. So this is the first restriction on the domain, but we're going to get another restriction of the domain here. The denominator can't be 0. Now this is just a line, and lines are allowed to be 0, but when this line is in the denominator of the function, it can't be 0. So let's go ahead and take the denominator and set it equal to 0 to solve for the x value. So x cannot be 3/2 or less than, or excuse me, greater than or equal to -1. Is that greater than or equal to -1? Let's see, so x has to be greater than or equal to -1. Oh, give me a second. So x has to be greater than or equal to -1, and it can't be equal to 3/2. So do these overlap? Let's see. Yes, they do. X has to be bigger than that. So the way that you would write this in interval notation, you could say -1 up to 3/2. And then parentheses and 3/2 to infinity. Another way you could write it is -1 to infinity, all the numbers bigger than -1, and x can't be 3/2. This is a little bit more compact. This interval notation is a little bit clunky, so this would be the domain of this new function here. All right, here we go. What do they want here? So this is a composition of two functions. So we want f circle g, or g into f. So you want to replace all the x's with g. So this g is x plus 2 squared. And 4x plus 1 is f. So here we want 4x plus 1 is f. So this f circle g is just f of g of x. And so we want to replace all the x's in f with g of x. So this is x plus 2 squared. That's g of x plus 1. So there it is. And then they do want us to write this in standard form, so we can expand it out here. So x squared plus 4x plus 2. I foiled, plus 4 plus 1. So this is going to be 4x squared plus 16x plus 16 plus 1. So we're going to get a 17 there. Now here, I think they want, I can't tell what this says. I think it's plugging in -1. I can't remember what the problem was. So we'll plug in -1. You could plug it in the final answer here. I think it's almost easier to do the composition this way. So we want to plug in -1 into f of g of x. So let's plug in -1 into g first. So if I plug in -1 here, I'm going to get -1 plus 2, or 1 squared is 1. So this is f of 1. Well, plugging in 1 in for x, for f of x, is 4 times 1 plus 1, so that's 5. I think that's a little bit easier than plugging in here, but you could also plug it in here. So if I plug in -1 over here, -16 plus 17 is 1, plus 4 is 5. So they simplify to be the same thing. So this is f of g of -1. Here they want us to apply the horizontal line test to determine if the function has an inverse. So I'm just going to draw a little sketch of the function off to the side. This is an absolute value function, and everywhere this function passes the vertical line test, but it does not pass the horizontal line test. So if I pass a horizontal line through, remember it intersects the graph twice. So this one is a no, it does not pass. This cubic, you might want to graph it in order to determine whether or not it passes the horizontal line test. So let's pull up Desmos here real quick. X cubed minus 6x squared plus 12x minus 8. And it looks like this passes the horizontal line test. It's a little iffy here at its x-intercept, but if we zoom in on it, we can see that it's pretty flat there. It doesn't double back. It looks like a horizontal line would only intersect the graph in one place at all times. So this is a yes. Here, this one, if we graph, let's just go ahead and graph it on a calculator rather than making a sketch, which my sketch would look pretty terrible there, is 4 over x. This one, too, looks like it would pass the horizontal line test, so that would be a yes. Horizontal line only intersects the graph in one place. And then a quadratic, we know that those look like this, and horizontal lines would intersect in more than one place. So this one is a no. So when a function does not pass the horizontal line test, that tells us that its inverse is not a function. So let's look at some problems down here where they ask us if the inverse is a function, and then they ask us to find the domain and range of the inverse if it is a function. So the way that we do this algebraically to find the inverse is to swap the x and y. F of x is y. So we're going to say x, y cubed. So remember, we swap x and y. We'll add the 16 to the other side. And then we want to cube root both sides to solve for y. So y is equal to the cube root of x plus 16 is the inverse of function. The cube root is continuous. It's not broken anywhere. We could plug it into our calculator here to see if it passes the horizontal line. So we could plug in the original function in to see if it passes the horizontal line test. And let's delete that one. And here we can see this green graph does pass the horizontal line test at all points. There's no place where it double backs on itself. A horizontal line only intersects in one place. So this inverse is a function. And the domain, well, x cubed has a domain of all real numbers. So I'm going to write, let's see if I can maybe write the domain of the original function here is all real numbers. And the range, we graphed it in Desmos, covers, the green graph covers all y values. So it's, oh, I can't get rid of that. Its range is also all real numbers. So we want to say, we want to swap these two for the inverse. So here, the domain is, or the domain is the range, and the range is the domain. So we are interchanging the two. Now here, a parabola up 2 that's downward facing does not pass the horizontal line test, so its inverse is not a function. So we don't even talk about the domain and range of the inverse because its inverse is not a function. Okay, here, the square root graph, this one is shifted to the right by 4. Looks like this. And this does pass the horizontal line test, so we can interchange x and y to find the inverse. So let's go ahead and do that. We'll square both sides. Add the 4. Okay, now the domain of the original, so this is the inverse function, so inverse is a function, yes, and it looks like this, f inverse of x is equal to x squared plus 4, but the domain is restricted. X, well, here, well, let's write the domain and range of the original function. So the domain of this original function, you can see the square root sketch that I graphed here. The domain is all x values to the right of 4. The range is all y values above 0. And so what that means is the domain of the inverse is going to be the range of the original function. So we want 0 to infinity. And then the range is the domain of the original function. So we want 4 to infinity. Even though x squared plus 4 is defined for all real numbers, we can't write that as its domain. We have to look back at the original function in order to find the domain and range of the inverse. Here's this one. This one is similar to part B, but we've restricted x to be less than 0. So the graph looks like this. I'll try to draw it nicely here. So here, the function goes down like that. Maybe I'll switch colors. There it is. And so this passes the horizontal line test at every point. So the inverse is a function, yes. And what it looks like is f inverse of x. Well, let's go ahead and solve. So here we'll have to swap x and y. So you replace f of x with x, and you replace x with y. And then we'll, let's see, what's the easiest way to do this? I'll add the y squared over and subtract the x over, and then square root both sides. So we're going to get plus minus the square root of 2 minus x. Now the question is which one do I choose? Do I choose the positive square root of 2 minus x or the negative? Well, in order to determine that, we're going to have to look at the domain and range of the original function. So the domain of the original function is negative infinity to 0. And the range, it looks like the highest y value is 2, so negative infinity to 2. So now we know that the domain is going to be negative infinity to 0. Whoops, that's the range. Let me erase that. So negative infinity to 2. So the domain is the range of the original, and the range is the domain of the original. So this one's going to be negative infinity to 0. So notice that the y values of the inverse can only return negative values. They're always less than 0. So what that means is we want this negative sign here. We want our y values of the inverse function to always be negative. We don't want the positive ones because my range, the y values should always be negative. So if I plug in a number like, say, -2 here, or 0 for x, one of those two values, the square root's going to return a positive value, and then the negative is going to make that positive value negative. So it's going to return a negative y value. So we want to choose the negative sign. The other way that you could look at that is you could just say, hey, look, we only have negative x's, so here our y's should always be negative. It's just kind of a logic jump there. Let's see how we're doing on time. We're about out of time here, so what I'm probably going to do is review this last section here with the step function with you guys live in class. So I'll have you watch this, and then we'll do some of these problems here when you see me in class on Tuesday. Okay, well, I'll see you guys then.